Okay, so we are going to go back to our KNearest Neighbors. I'm just going to copy and paste a little bit of the code that we had in last class. So the libraries, which you guys can copy and paste, and then we had this Disney data set, or Disney Plus data set. And okay. We created a filter so that we were just looking at the movies that were rated between R, BG 13, BG, and G. And then we were looking at run times of less than 3 hours, 20 minutes, and ratings above 3. Okay. And we had, importantly, this guy here, this Disney.new, which is kind of the matrix of all of the values that we want to predict on. That's how we were creating that sort of prediction map that we were seeing last time. And okay, as a quick refresher, our KNN, this was what we had entered to look at this, which led to having this plot. Okay, so let me run all of this. Uh-oh. Disney.filtered. Am I in the right directory? I am not. Okay, let's try that again. Okay, so this is where we ended last time. Where is... Okay, so as a quick reminder, right, the way that KNN works is pretty different from anything we've done so far. Essentially, all I need to do here is look at the distances in any point to my sort of nearest neighbors. Okay, there is something kind of interesting here, though, that I hadn't mentioned last time. So if the KNearest Neighbors looks at Euclidean distances from any sort of point, is there anything kind of odd about this plot that you guys can see here? Okay, let me put it another way. So what happens if I took this same plot and I just squished the y-axis? How would that affect, for example, if I say, okay, what are my nearest neighbors to like this point? What do you guys think?
It makes things that were further up or down the y-axis closer.
Exactly, right? So like, let's say I was here. Let's say I'm right here. Okay, I am equidistant. Let's say I'm equidistant from this guy and this guy along my x-axis. And then it's equidistant from this guy and this guy along my y-axis. But that distance we're looking at is just visual, right? That's just a fact that we've decided to display this in terms of a plot that takes up the whole space, right? So if I decided to squish these together, then if I say here, even though it's equidistant from blue, blue, and these guys, suddenly these two guys look a lot closer, okay? But it's not as though the KNN algorithm cares about the distances based off of how we graph it, right? It's looking at Euclidean distances. So let's look at these axes. Which one of these do you think makes a bigger difference?
Definitely runtime because the range is so wide.
Other way around, because the range is so wide, it looks like they're really far, right? So that means vote rating is going to have a sort of bigger effect. So this is something to keep in mind when you run a KNN, is the scale, right? This is going from 0 to 200. This is going from 3 to 10. That can make a big difference. And so oftentimes, if you want these things to be roughly weighted the same, then you'd have to do some kind of scaling before you run the KNN. Okay, so let's take a look across a range of different Ks. So I'm going to make a for loop to do this. And let's just look from K in 1 to 10. And I'm just going to run this a few times. So this is going to be exactly the same code from the first KNN. Actually, I'm just going to go ahead and copy and paste it. That'll be a little bit easier, a little bit faster. So I take this code here, which is what generated our KNN results from last time, and I'm just going to add it here. But now, instead of saying that we only have 3 neighbors, I'm just going to say we have K neighbors based off of our for loop. We'll update this thing called hold. Okay, so this table that I'm defining inside the for loop is creating this temporary table. And it has a column of my runtimes, a column of the ratings, of the new runtimes and new ratings from that matrix that we're going to predict on. It'll give what K that is, and then it'll get the predictions. And all we do here is update this KNN example from the outer loop to grab this new data. And that's it. So let me go ahead and run this. And so what do we get? We end up with something that looks like this. So this is our mapping for all the possible combinations of runtime minutes and ratings. And then with one cluster, and then the prediction at that particular point. So this is giving us essentially these maps, but there's going to be 10 of them, right? One for one nearest neighbor, one for two nearest neighbors, and so on and so forth. So I can take this and plot it. So I can just grab the ggplot from before and modify that. So here I'll copy and paste my ggplot. And I'll change my data so that I am looking at, let's see here. Instead of Disney new, I'm going to look at knn.example, and everything else should be the same. Okay. And then at the end, I'm going to add a facet wrap. Okay. And that should give me the plot of all 10 of them. So let's wait a second for these to plot out. Hopefully. Here we go. Okay. So this is my plot with one neighbor. Let me make this a little bit bigger. And it has to re-render. So we'll wait another moment. This takes a while because there's so many points here, right, in the back. Okay, so as we go from left to right, you're going from fewer neighbors to more neighbors, and then top to bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And essentially, what you have going on is in the first nearest neighbor, you're looking at just the closest point, right? And then you're looking at 2 closest points, 3 closest points, and we can see kind of how the plot is changing over time. Probably most notably, like even here, if you look kind of in the bottom left quadrant, right, the amount of red is kind of increasing. So here you might have a couple blue, like one blue point really close by, but then here, it's going to see that sort of surrounding that, maybe there are more red points. So I think there's about 700 points here. And as we talked about last time, as I crank up the number of Ks, the more and more sort of homogeneous this is going to look, because eventually it's going to get to the point where everything becomes just one category, right? Which is whichever one of the categories has the most points. Okay. And your decision to select a particular K, right? We talked about this. You can figure this out based off of cross-validation. So I could leave out a couple of points and run through a bunch of Ks, put in the test one, put in the ones that you left out, see how well it predicts. And then you want to do this many times, basically until you figure out which K does the best at predicting those guys correctly. Okay, any questions? All right. So we will get on to the main topic of today's lecture. All right. Okay, I'm sure a lot of you guys have heard of this before. Correlation does not equal causation. More fundamentally, we're going to start to talk about the sort of distinction between these two sorts of approaches that are focused on thinking about causal effects and things that are focused on prediction. Okay, and so if you are more of, let's say, an economist and you're doing kind of econometric models, you're going to fall much more into the camp of like trying to figure out causal effects. So one thing is leading to another. Okay, that's different from, I would say, traditional sort of machine learning, which cares less that a particular X is leading to Y. Maybe they care more specifically about being able to predict a specific outcome. And we're going to start to see that the models are sort of geared this way to achieve these outcomes. We already have started seeing a little bit of this, right? So, for example, in like a linear regression, the simplicity of the betas and the slopes allow for you to interpret pretty easily a relationship between my X and my Y. Okay, but let's say if we were doing like the principal components analysis, the PCA, like those coefficients don't really mean anything. The main thing that they care about is figuring out the Y outcomes, right? And so we'll start to see more and more how the trade-off in sort of the model approaches allows you to do allows you to focus more on causality or allows you to focus more on getting good predictive outcomes. So just to be clear, so we're going to focus on causation today. So correlation is a relationship between two variables. Okay, and so everything that we've talked about is kind of more along this these lines. We haven't really talked about causality yet. And so when we think about this idea of y is equal to beta x, and we say, okay, an increase in x, the value 1 leads to y increasing by a beta amount. That is simply saying that we observe this type of relationship in the data. It doesn't mean that if you go out into the real world and you forcibly change x by 1, that y would necessarily change by beta. Okay? Does everyone understand that distinction? Okay, we'll have some examples that hopefully will make this a little bit more clear. So causation, one event is the result of the outcome or of the occurrence of the other events. Okay. So one of the things that we're going to use to help visualize this concept is known as a directed acyclic graph. This is also known as a DAG. So in mathematics, this is known as a finite directed graph with no directed cycles. And all that means is you can't loop. Okay, so let's take a look at this. Let's do an example. Frequency of brushing teeth. Okay, so what we have is something like frequency of brushing your teeth leads to some amount of variation in gum disease. This can have some inflammatory immune response, which can lead to sort of heart disease. Okay, this is actually based off of real example studies. just as nomenclature, when we're talking about the DAG, this is known as the parent, and this would be the child. And then you have just generally going up the tree, you have ancestors, and going down the tree, you have descendants. Okay. So we look at this data and we see this very strong relationship between how frequently people brush their teeth and instances of heart disease. And we even have kind of like a mechanistic chain of events that makes sense that kind of lead to this. Okay. So what do you guys think? Does brushing your teeth improve your heart health? Why not? I see you shaking your head.
I can't think of any direct link.
Well, the direct link's right here, right? These are all known to be true. Yes. Okay, what do you mean? Okay, yeah. So your diet might be driven by your health consciousness, frequency of exercise. So it turns out you're exactly right. There's like other stuff that also contribute to your heart disease. So even though I know something about the frequency of brushing my teeth, maybe that is a result of someone who is health conscious. And as a result, if you're health conscious, you also exercise a lot. You also have a good diet and you brush your teeth. And so all of these things contribute to heart disease in some way. And suddenly the idea that this is leading to heart disease is confounded by the fact that there are other variables that are contributing to this outcome. Okay. So this is where I'm talking about the kind of distinction between something like machine learning or approaches that focus on predictive outcomes. I don't care that there's other things going on. This, in fact, I could think of as kind of a proxy that I'm able to measure for health consciousness, because you can't really measure this very well, okay? And so I have thousands and millions of records of this, thousands and millions of records of this, and I say, hey, this is a pretty good way, this is a pretty good metric for me to figure out heart disease. As opposed to the world where we say, I actually want to know specifically how brushing your teeth leads to heart disease. And I want to be able to separate this guy from these effects. So conceptually, if we think about this, let's say this is the whole world, okay? Nothing else exists outside of this. how might you modify this plot in some way to start to think about the causal effect of this on this? If, let's say these arrows are kind of law, okay? These arrows indicate causality. So yeah, you raised your hand.
I was going to suggest we start with the arrows at the bottom and see which of those three, frequency of exercise, amount of red meat, and inflammatory immune response, what their input is to heart disease.
Yeah.
And then sort of calibrate it up.
Yes. Okay. That is one way to do it. What is that called? One sec. So you want to you want to block. So this is called backdoor. So you want to block all of the indirect paths of X to Y, which means by controlling for these, you can essentially block the effect of these guys in your health consciousness. So yeah, that's one way to do it. Another way is to essentially try and remove this. And we'll talk about sort of how you go about doing that, right? And so if you have kind of a good conceptual idea of ways that you can manipulate this, you can kind of logic through the different strategies that you might take. And so in a lot of these causal models, that's essentially what you're doing. You want to be able to do things like break this relationship, because right, if this were gone, then we would know that changes in this, there's nothing else leading to changes in the heart disease that we're observing through that pathway. The trick, the difficulty with doing the backdoor method is that oftentimes this isn't our whole world, okay? And so if I control for these two, I don't know that there's a bunch of other variables associated with health consciousness that might be affecting heart disease as well. Okay. Any questions about this? Okay. So let's generalize this problem a little bit. Yes.
What you said here, that frequency of expression is whether it's more or less, it does not cause an impact on that. But if we establish here that there is absolutely no correlation between.
I'm not sure I follow. So you need there to be some kind of variation in your outcome related to variation of whatever it is that you're interested to even observe a correlated effect. The causation means that we are making sure that changes in your outcome are only related to changes in the variable that you're interested in without there being other variables affecting that. Yeah.
So basically, both can come into play when we are kind of analyzing this, like a real-time scenario that we analyze. If the increase or decrease in incentives for electric vehicles adoption will change, is that a causation or a correlation?
Yeah, so the idea is like you observe that there's incentives for electric vehicles, and you observe that the sales of those vehicles increase. Okay, but let's say you're observing this over time, right? That is not a causal effect until you've demonstrated that there's nothing else causing the sale of EVs to increase. So for example, let's say that some dealership is selling on average like 100 cars, 100 EVs a month. And then some incentive kicks in, and now all of a sudden you see them selling 150 cars a month, and you say, oh, hey, this incentive is causing a 50% increase in EV sales. But what you didn't realize is that gas prices also went up by some amount in that time. And so is it coming from the incentives? Is it coming from the gas prices, right? And so, yeah, you have to be really careful to be able to extract a causal effect.
Like when we have to do it all the time for the other, that is when we consider there to be expert.
Yeah, let me talk about that in a more general way. So general problem looks something like this. So we have X's in our data, and we have Y's in our data. And we want to understand the causal effect of X on Y, but there's a bunch of unobserved variables that could be influencing X and could be influencing Y. And so we say that U confounds effect of X on Y. So in general, we think about something called identification, which is the strategy to remove the confounding effect. And determine the causal effect. Okay. So what are three general strategies we can take here? So one, block all indirect paths from X to Y but leave all direct paths open. So this is known as a backdoor. Here, let me move this down. Two, all direct paths from X to Y pass through a mediator variable. This is known as front door. And three, and by far the most common, is to use an instrumental variable which affects X and affects Y only through X. So the reason why some of this works, so causal inference only flows in one direction, but statistical information can flow in either way. So in other words, you can infer an effect from its causes, but we can also infer causes from their effects. This starts to stray into some statistics that we're not really going to get into. But that's kind of what allows for some of these properties to work. So an example of the backdoor might be something like this. Where you have a mediator variable which is unaffected by your unobserved terms. So the reason why I say like 1 and 2 are a lot less common is that finding a good mediator variable is very, very difficult. Okay. You can imagine that, like in the last example that was just here, we had frequency of brushing your teeth, going to gum disease, going to inflammatory immune response, going to heart disease, right? And it's unlikely that something like gum disease would be a good mediator variable because maybe that in itself might be affected by your diet, for example. So there's tons of other things that can go into it. So really here, you don't want anything to interpose, because if you have this, suddenly your causal effect is, your causal link is going to break. So the most common one is to have an instrumental variable. So that looks something like this. So this is a sort of valid example. And so essentially the idea is that I want something here that affects X and it affects Y, but it affects Y only through X. Okay, and so this would be an invalid instrument because now this is also affecting some kind of other variable. So this is a classic technique used by lots of economists to try and elicit a causal effect. This is a common identification strategy. And it's definitely more, I would say, art than science. If you ever go hear a talk where people are talking about causality, a lot of the time they spend a lot of time in these presentations essentially defending the instrument, right? So what does that mean? That means kind of qualitatively arguing that the relationship looks like this and that you don't have sort of other effects that would break this kind of relationship. Let me give a concrete example from a paper that I had published many years ago. Okay, so we have our X and our Y. So this is gas prices, and this is VMT, which stands for vehicle miles traveled. So gas prices affecting how much people drive, essentially. Okay, so I want to know the causal effect of a change in gas prices leading to changes in people's driving behavior. So let's forget about this for a second. All right, who wants to comment about this model? Right now, based off of our discussion, right, what we have in this diagram is not a causal effect. And so why is that? What might be some things in here? Yeah.
Pandemic lockdown.
Yeah, okay. So gas prices are changing. You got differences in how much people are driving, but you didn't foresee the fact that, okay, there's also these lockdowns and no one's driving anyways, right? There are like tons and tons of reasons why your travel behavior might be getting affected. And not having to do with anything about gas prices, right? So this might be pandemic lockdown. What else? What other examples? Yeah. Time of the year. Yeah. Anyone else? Other examples that might cause your driving patterns to change a little bit? What? Telecommuting. Yep. So the problem is, like, even if I attempt to control for these guys individually, there's probably just too many things that you can observe that are changing the VMT. So we need to come up with a clever solution here with some kind of instrumental variable that we know can affect gas prices, but that don't affect like this. This also can't be a thing, right? It can only affect your outcome through the variable of interest. Yes.
How do you know you're not like manipulating the relationship to the point where you're creating publishing? Or is that like built into just how it works? Basically, if you you know you're not inputting bias into the output. Like if I just made up a relationship and somehow it works, how do you
Well, what do you mean make up? You mean like add this?
Yeah, or if somehow that IV on the left
Yes.
does affect that similar travel later, and then it does affect vehicle miles traveled too. Is the model?
Yeah, it can't do that. Yeah, well, no. So if it does do that, then your argument that you've done a proper identification strategy is no longer valid. So people spend a lot of time like defending the fact that there isn't anything funky going on here. Okay. Yeah, and in fact, if you go to a sort of proper like econ presentation that does this type of thing, I guarantee you like more than half of it is going to be talking about this thing that you're trying to point out, that like the IV like really definitely doesn't affect VMT through anything other than gas prices. Can anyone think of an instrumental variable? Oh, okay, yeah. Okay. Oil prices. Okay. So what would your argument be that this is what's happening? Mm-hmm. And this, yeah. So you have to make some arguments that that this guy isn't going to affect VMT through anything else. There is some argument that VMT itself could affect oil prices. It's a little bit more far-fetched because it'd have to be a kind of extreme situation, right? But the idea is like, let's say that everyone stopped driving. What do you think happens to oil prices? Would they change? Oop. Probably oil prices would change, but okay. That might lead to changes in oil prices, but it might be kind of a fringe example where you say, hey, there might be some kind of relationship, but it'd be so kind of far-fetched that we wouldn't expect that to happen. But a lot of people would argue that there is kind of this relationship. Yeah. Okay. What? Yeah. Yes. Okay, good. So you are in fact kind of doing the same thing, but you are narrowing down. So war leading to oil price changes. And so your IV would be something like this. And this would affect gas prices, but it wouldn't affect VMT. Yeah. So actually, we did something similar in concept here. We looked at gas prices in Pennsylvania versus hurricanes in the Gulf Coast shutting down refineries. Okay, so this is an IV which might affect gas prices in Pennsylvania, but it's far enough away that it's not like people are driving differently because there's a hurricane in the Gulf. Okay, so similar concept to what you're talking about with gas prices changing through war. And so there's a whole bunch of other things that might be affecting gas prices, but essentially what we're going to do is run a regression so that we are observing only the changes in gas prices. Okay, so we're going to do what's known as a two-step regression to examine this. Before I get there, one thing that I wanted to mention, and one of the fundamental problems with this is that you could have a really good instrument and a valid instrument, but there could be a pretty weak relationship between your IV and your gas prices, for example. And as a result, you might have a lot of noise here, which means even if you determine a good causal effect, you might not be so good at predicting. And at reasonable sample sizes, in fact, not doing the IV could actually lead to better predictions a lot of the times because of this effect. Okay, so that's something to keep in mind. You can you can introduce a lot of noise into your model when you add an instrument like this. Okay, any questions about this?
Are you looking at the third method here?
Yes.
And second method you mentioned is the mediator variable is the hard, like the hard to define. Probably not the.
Yeah.
What about the first one?
Same idea. It's hard to get. It's hard to create these relationships in 1 and 2. These are relationships that you can demonstrate statistically allow you to get causal effects, but practically speaking, number 3 is kind of the most common. Okay, any other questions? Okay. So we are going to look at implementing this. Talk about how this actually happens. 1 sec here. Okay. So we're going to work with a real data set. I guess we're squaring these for some reason. Don't worry too much about that. So gender. So we are interested in this variable. Interested in causal effect. And what we're going to do is we're going to look at 3 different possible instrumental variables. So we have possible IVs. We have a cigarette tax, unemployment, and whether or not they've been separated or divorced. Okay. So as I think about possible instrumental variables to determine the causal effect of being a smoker, what are we looking for? We are looking for these things to affect BMI, but only through whether or not they are a smoker. So what do you guys think let's talk through this. Instrumental variable of being separated or divorced. Is this a good instrument? You're shaking your head, why not?
Just thinking about actually how that fits there. There could be a lot of noise between
So think very specifically here that we want this to look like this. Okay.
It can also directly affect BMI without this.
Okay. Yeah. So we're arguing that maybe there is something here. Maybe. But probably more reasonably, you could say, yes, that it's affecting, right. So probably the fact that you're separated or divorced will have some kind of relation to whether or not you're pregnant, right? So it's likely that if you are separated or divorced, there's probably a lower chance that you're pregnant, maybe. We can imagine that there being some kind of relationship here, in which case this variable would no longer be considered a valid instrument. Does this make sense? So what about unemployment? Yeah. So now we're saying, whoop, there's probably a relationship between the fact that you are unemployed and your income. Okay, and so in this case, yeah.
Wouldn't the same go for, well, rather, wouldn't there be another direction? Age should affect unemployment as well, right?
Yes, so different type of thing. So let's say, well, okay. Yes, that's right. So if you have something like this, so even if unemployment didn't have this income thing, having this would break the validity of your instrumental variable. Okay. So what about cigarette taxes? Do you guys think that people's higher or lower income or their age, gender, whether or not they're pregnant or their education will affect the fact that a cigarette tax was implemented? And then do we think that a cigarette tax would affect your education or the fact that you're pregnant or all of these things? Probably not. Okay, and so the argument then would be that this will affect your BMI, but only through the fact that you are a smoker. If somehow a cigarette tax caused the general population to be sort of really anxious in general, and they get worried about it, even though they're not, they may or may not be smokers. And let's say it causes people to like exercise or something, right? Like then this wouldn't be a valid instrument because then it would be affecting BMI through some other way, right? But that's probably implausible. And that's the type of thing that you would spend time kind of defending your instrumental variable on. Yes.
I have a question. So how did you choose those possible variables there? But there's, in terms of smoking, there's also studies that link to race or education or sexuality.
Yeah. So in this particular example, this is getting drawn from like a data set that people, it's an old paper that was looking specifically at this problem. And so it was kind of a demonstration case of looking at different possible IVs. And so, I mean, there's certainly other things kind of going on in this sort of world that could affect BMI. But the whole idea is that like, we just need to find one sort of plausible instrument to determine the effect of smoking. So let me walk through in practice how you would, we've been talking all about IVs in concept, which is kind of the most important thing here, because you really want to understand the validity of the instruments. So in our traditional model, we have an OLS, which is y is equal to beta x plus epsilon. And then we're going to look at something called 2SLS, which stands for two-step least squares. Two-step least squares. Oops. Okay. This is step 1 and step 2. Okay, what the heck's going on here? So in an OLS, if I want to determine this relationship, I run a regression of BMI on smoker. And okay, and maybe I'll control for other things too. But if I'm interested in the causal effect, I want to know how changes in whether or not you're a smoker affect BMI. So what I'm actually going to do is run a regression first of cigarette tax on smoker. And I'm gonna figure out how this changes this. And then I'm gonna run the regression again, leading to this step where now you are using x hat instead of x to determine its effect on BMI. Yes.
As like what's the speed the person's in, and if there was cigarette taxing.
That's actually how this is going to happen. Is we're going to look at different places that have different cigarette taxes, so that we have variation here and variation here. So the idea here is now I'm essentially saying we're doing this, and then we're doing the predicted values of smoking coming out of here in order to determine how those changes that result only from the cigarette tax affect BMI, which then we're arguing is the causal effect, right? Because then we know that there's sort of nothing else affecting this besides the cigarette tax that's leading to changes in BMI. So this is a nice kind of elegant, simple way of doing of executing our sort of theoretical construct to get at the causality. And once you do this beta, that's the thing that people are after, right? This beta is now telling us the direct cause of BMI changes from being a smoker. Okay, any questions about this? Yeah. Yeah, so that is getting into okay, what I'll say about that. So doing those approaches are also ways of trying to get at causal effects, but it's using a slightly different technique. We can talk about that. That's not something that is currently planned as material for this class, but if we have time, I can add some material on that. Yeah, there's some concepts related to structural equation modeling that I can't just explain right now. It would probably take a little bit too long. But I'll see if I can fit. Yeah, if there's time in the schedule, that can be a topic that we choose to cover. Yeah. Okay. So let's have a go at implementing this. So I've already uploaded a data set. So if folks wish to follow along, you can go find that on Canvas under the lecture 12 files. Share my screen. Oops. BMI data. I'm going to use read table. Oops. I need to. Oh, I guess I'm using read table, which is the base version because of that tab separated. Yeah, I don't remember if fread does that. Well, okay, you could probably do it with fread as well. And in fact, we'll just go ahead and change that to a data table here. And I'm also going to just remove all of my NAs. Make this slightly easier. Why do I keep typing C instead of B? Okay. No. Complete case. Oh, need a comma at the end. Great. So let's take a quick look at BMI data. We have ST-FIPS, which is an indicator for a particular location, year, income, income squared, age squared, whether or not they're female, whether or not they're pregnant, education, I believe that's years of education, whether or not they smoke, whether or not they've been separated or divorced, whether or not they're unemployed, their BMI, and then the cigarette tax. So all of these things that we have over here. So let's take a look first at the OLS example. So LM, so we're going to do BMI on income squared plus age squared plus factor female, factor pregnancy, factor education, and factor smoke. Data is going to be coming from BMI.data. So I'll run that, and let's take a look at the summary. Okay. So we observed the coefficient values and then the statistical significance things, right? So anything lower than, let's say, 0.1 over here is significant at some level. So this is saying age and gender seem to be important factors for BMI, makes sense. And here we can see whether or not you're a smoker has some effect. It's not statistically significant, but looking at the size of the effect, it's basically saying it's 0.29 in comparison to, let's say, gender, which seems to be kind of a sort of larger effect. Okay. But so we can argue, right, that this is not, this is just a sort of correlation. We haven't sort of tried to control for causality in any way. There's probably some other, there's probably some other stuff going on here, right? Like this could be a thing. This could be a thing. And so the IV is going to help us separate these other issues out. And this is probably a thing as well. So let's just do 2 examples. Let's do IV to SLS example with unemployment as an instrument. So what do we do first? Stage one. Our first stage, we're going to regress on our causal variable of interest. And because we might suspect things like this, where income might affect smoking, age might affect smoking, we're just going to go ahead and control for all of those guys. So smoke, income squared, age squared, and all of the other variables in our model. And then critically, at the end here, I'm adding in our instrumental variable. And what I'm going to do is I'm going to add in a new variable into our original data table. And that new variable is going to be my x hat. Okay, so I'm going to run this. I'm going to do the predict function to get my x hat, and this is now going to get added into the table. And then we're going to run our two-stage, or our second stage. So this is the first stage. And I've now done my prediction for my x's, and I've added it into the original data table. And now I run the regression that we had just looked at in the OLS example. So this is going to be stage 2. Okay, so this is going to look exactly like our OLS, except that instead of having factor smoke, I'm going to include the predicted value of being a smoker. Which we predicted based off of unemployment. Okay, so let's take a quick look here. So here's where we want to be a little bit careful. So once you've done this, remember before in the OLS, the gender was an important factor. But it's now statistically insignificant, and the coefficient size is much smaller than it used to be. So I guess the argument here is that they're saying, actually, the thing that's making a big effect here is being the causal effect as we use this unemployment instrument. And so this is like a big effect here. right, relative to what we had before, and now it's statistically significant. So you need to be really careful here, because when you implement this IV, it can bias the model a lot. And unless you're certain that this is correct, that this is a valid instrument, you might be dangerously biasing your model. Okay, yes. Yeah. So it's pretty common practice to just throw in all of your other X variables in order to deal with this issue that you might have other things happening to smoker that you might as well control for. So these, like if these are a real thing, yeah, so you're talking about looking at the vector of coefficients here to determine whether or not they should be included. Yeah, you can, but it's not the idea. The main idea is that if it's a valid instrument, those things probably wouldn't affect it that much. So it's kind of a thing that you might as well do. Okay. Yes. Yeah. Okay. So let's go ahead and do the one that we think actually makes sense. Okay, so in our first stage, we're going to do the same thing where we're regressing on our variable of interest, smoke. And we're going to do income squared, age squared. And then at the end, we're going to have our cigarette tax. We're going to create this new predicted variable, and that's going to be our predict. And then we'll go back to our original model as our second stage. And let's have a look at the results. So let me run all these guys first. Error in factor. This factor is not a variable, or not a function. Factor, great. And And okay, actually. So one thing I forgot to mention, we actually shouldn't be looking at the statistical significance here, because in the way that we've done this, you've actually introduced all of all the other control variables in your first stage, which is actually going to affect the standard errors in a certain way, which you can control for, but in this case we haven't done that. So I'm going to show, so this way that we're approaching the 2SLS, we are manually doing this, and again, this is as a way for me to kind of make sure that you guys understand the steps of doing a 2SLS. But the word of caution here is that your standard errors are actually going to be too small because of the sort of statistical relationship that's happening here with your other variables. And so I'm going to show there are packages that do 2SLS for you so that you don't have to manually do these one step at a time type of things. You could just do it sort of all at once. But this way we can see what's going on. Okay, and so here we observed there's an even sort of larger effect. This is E2. So the causal effect of being a smoker on BMI turns out in this case to be sort of rather large. Yes. Yeah. Yeah. That's where the art of it is, rather than the science, is that you have to spend time, like, so this foundation that I walked through theoretically before about these arrows and their relationship between your variable of interest, your IV, and your outcome, like, hopefully you can see that those things must be true to be able to validly say that it's a causal effect. Okay, and so the difference is that between this model that we just looked at, it looks very similar to the unemployment one. But unfortunately, in that case, you would essentially say, well, unfortunately, I know that that's not a valid instrument, and so we can't say anything about its causality. And so whatever number that was, it's like, that's just a relationship that we observe, but it doesn't mean that changing one changes the other. Whereas here, you might more validly be able to say that. So it's more about understanding the causal relationship than necessarily about the sort of size. Well, I mean, the size is kind of part of what you're looking for. But again, going back to the initial concept, if you are mainly concerned about like predictive measures, then yeah, if you're mainly concerned about predictive measures, then there are other sort of techniques to even be able to predict your outcome better than, you know, these linear regressions. Okay. So last thing we're going to do today, really quickly, I'll just show how you can do this with a built-in package. So AER is a package that does this. And the way this is done is with a function called ivreg. And you write your equation as regular. Oh boy. Right up until we add our variable of interest. And then here, you add a vertical line, which is an indicator that, hey, I want to do an instrumental two-step and regress smoke on all of these guys. That's kind of the unique syntax here. And that's it. You run this and you're good to go. You get your results. And now you can see identical coefficient here, 1.372. But the standard error leads to a much, so the standard error is much larger. It's 1.18 to the third power compared to 9.8 to the first power, or e to the 1. Yep. So this is where you're introducing kind of a lot of noise into the model. That's an artifact of having to do the first stage. Okay, and that that'll conclude our lecture for today. We'll end here, and you can take this last example as a sort of more practical way of doing 2SLS without manually doing each step. Okay, thanks all. I'll see you guys next week.